which happens to be inverses. So basically, let's say, okay, so this is what we've been doing so far. We have our u and v plane, right, and our d naught. And we take points from here and send them into the xy plane. So xy is over here, and then we have some other thing. Okay, so this is d. And g is doing that for us. So g takes us this way, u, v. But now, let's say we have another function which allows us to go this way, allows us to go backwards, take points from the xy plane and send them into the uv plane. And let's say that one is called f, and this will be f of xy, right? So then in this case, our f of x comma y would equal u, depending on x and y, as a function of x and y, and v as a function of x and y. So it's basically just swapped around the variables. But anyways, in this case, just like in, I think, algebra 2 and stuff like that, like high school algebra, anyways, the relationship between the functions g and f are that they are inverses of each other. So g is the inverse of f, and f is the inverse of g. Okay, and what that means with reference to our Jacobians is the following. Jacobian of g equals the inverse of the Jacobian of f. Okay, so what this means is that, well, I'll write on the next slide. So Jacobian of g being the inverse of Jacobian of f just means that this -1 means it's flipped to the bottom, right? It's an exponent of -1, so that means it goes to the bottom. So that just means it's 1 over Jacobian of f, all right? So this is, remember the term reciprocal, there we go. So that's just useful to know when it's easier to go from, not from left to right, but now from right to left, sending points from the xy plane into a different coordinate system. Okay, so let's do a final example of that. So we'll have integrate, and they give us f of x comma y equals xy times x squared plus y squared over, and they give us the domain. D is defined by -2 is less than or equal to x squared minus y squared, less than or equal to 2. And then 1 is less than or equal to xy, which is less than or equal to 4. So in this case, it just so happens that there is a, I guess, relatively simple, a simple map. So G or F or whatever you want to name it. I'll just call it F since this one's actually going backwards. So this goes in the, I guess you could call it the wrong direction or the opposite direction, basically, because we're starting with a xy point, and we're going to be going backwards into u and v. So what we're going to do first step, is going to let u equal the following: x squared minus y squared. And the purpose of doing this is to simplify this part right here, this interval. See that? So basically what we can do is replace this x squared minus y squared and replace it with a u. So then we have simple bounds, all right? Something simple on the inside. And then we're also going to let, similarly, this part here we can simplify by making v equal to xy. So then we can write 1 is less than or equal to v is less than or equal to 4. Okay, so keep this in mind, and we will continue on the next slide. Okay, so again, I'll rewrite the intervals here. So we have u going from -2 to 2, and v going from 1 to 4. Okay, so let's map that out here. So we'll have our uv, now we're in the uv plane, right? So uv, and then we have -1, -2, +1, +2, 1, 2, 3, 4. Okay, So negative 2 to 2, and then this is 4 up here. So, whoa, that was a weird 4. Okay, so we have basically a rectangle being formed, and this is our D naught. All right, so everything in here, that's our domain, D naught. Okay, and then what this actually looks like in the XY plane, I'll just sketch out real quick here. I don't know the exact points and stuff, but you can look in your book for a more accurate picture, because this might not look too pretty, but we'll see. So it looks something like that, kind of. It kind of reminds me of like a basketball. But anyways, this is x squared minus y squared. This is when we were in x and y still. This is negative 2, and x squared minus y squared equals 2. And this is a similar example, as I mentioned, from your book, except for they use negative 3 and 3, and I just used 2's instead. And this is x, y equals 1. So basically what we're looking at in here is this region. This is our D. Okay? And somehow f, our function, takes it from the xy plane to the uv plane. Okay, so f is doing this. That's allowing us to do that. So what we need to find is, what we're concerned with is g. G going from left to right. So g takes us from uv into xy, somehow like this. Okay? And typically what we would do is take our function of uv, which would require us to know x in terms of u and v and y in terms of u and v. But we don't know that as of now. It's hard to invert these functions. So what we're going to do is kind of use like a, not a shortcut, but a back way. Yeah, just like a back way of doing it, going through f instead. So we're going to make use of the relation that Jacobian of g is equal to 1 over the Jacobian of f. So if we find the Jacobian of f, then we'll automatically know Jacobian of g, which this is a pretty useful relation actually. So I'll continue on the next slide. So our f, what is f of x and y? This will give us u in terms of x and y and v in terms of x and y, right? And remember we made u equal x squared minus y squared to make the bounds simpler, and v equals xy. So basically that's all we're going to do is plug in this for this spot and this for here. Okay? So this is what it's going to look like, x squared minus y squared and xy. Okay, so this is our f of x comma y. This is moving from the xy plane to the uv plane. Okay, so from here we're going to compute the Jacobian of f, and this is going to equal, okay, so this might be a little bit trickier because I'll label these up here. So this is an important part up in this box here. This is u of x and y. Okay, so a function of x and y determines what our u value is, and v is the same thing. Okay, so what we're going to do is, now we're looking at it differently. So we're going to take the first one, so u, so partial of u, partial x, that's our first variable that it depends on, and then we're going to write partial u, partial y. And then same thing here, but now with the v function. So partial v, partial x, partial v, partial y. Okay? So let's solve for these. Let's fill in the spots. So partial u, partial x, if we differentiate this with respect to x, we just get 2x. Okay? And then if we differentiate it with respect to y, we get negative 2y. Now let's do the same thing with v. Partial v, partial x is going to be, we're holding y constant, so it'll just be y, because that's like, think of y as like 2 or something. And then partial v, partial y is going to be the opposite, which is x. Okay, so now we're going to continue computing, and we take the first diagonal, the product of the first diagonal, so that's 2x squared minus, that's according to the formula, the product of the second diagonal, which is negative 2y squared. So what we get, these negatives turn into positives, and we can factor out a 2. So we get 2 times x squared plus y squared. Okay, so this is the Jacobian of f. That's what we just calculated. So that means that Jacobian of g equals 1 over what answer we got. So that would be 2 times x squared plus y squared. Okay, so now we have all the tools that we need to compute the double integral, right? So we have, again, I'll rewrite it here. U is going from negative 2 to 2. V goes from positive 1 to positive 4. This is our Jacobian here. And we can put absolute value signs on it, right? Absolute value, even though it doesn't need it because x and y are both squared. Anyways, so that's that. And then we also know that our f of x, y is equal to xy times x squared plus y squared. So we're just going to plug all of this in and see what happens. Okay, so our double integral of f of x comma y dx dy is equal to the double integral over d naught. And d naught, again, that depends on u and v. All right, so what we're going to be doing here, again, is what we've been focusing on, is a change of variables from x and y to u and v. Okay, so this is going to be f of x depending on u and v, and y depending on u and v. And then we have our Jacobian here. That's where we're going to insert this circled thing. And then du dv, or dv du, whichever way you want to put it. So what we're going to have, I guess I'll just choose the v to be the outer. So I'll put the v here, so that'll be on the outside, dv. And then we have du stuff, so then du here. And then we have, I'm just going to leave this part, I'm going to write that in, not in terms of u and v yet. So I'll just leave that here, like that. So xy, x squared plus y squared, and you'll see why. So then if I insert the Jacobian here, this is 1 over 2 times x squared plus y squared, right? Which is super convenient because then we can cancel out these two parentheses, these two quantities. Okay? So I'll continue on the next slide. So what we get, I'm going to put the 1/2 in front, okay? And then we just rewrite our bounds here. And we're left with xy, right? du dv. So now if we want to put it in terms of, now we want to transform this into u and v. So remember v equals xy. So that just becomes a v, this circled thing. So then we get 1/2, 1 to 4, negative 2 to 2 of v du dv. Okay, and as you can see here, since we have constant bounds on everything, this is an iterated integral. Iterated integral. So that means we can split it up. So we're going to have 1/2, and then all, let's see. So we have to make sure the bounds stay with the differentials that they correspond to. So du is going to be from negative 2 to 2 du, and then I have everything else fitting into the v parentheses. So we get 1 to 4 dv, and the v goes with it. Okay, so then we get 1/2, and then we'll get a u goes from negative 2 to 2, and then we have a 1/2 v squared going from 1 to 4. All right, so what this turns out to be a 1/2 2 minus negative 2, so that would be 2 plus 2, right? So 2 plus 2. Okay, then we have a 1/2, and then v squared, so 4 squared minus 1 squared, and this is 4 over 2, so this turns into a 2, which cancels with this 1/2, so that gives us 16 minus 1, which equals 15. Okay, so that is our answer for that problem. And now lastly, so we've gone over change of variables now, and this was specifically for moving from one plane to another. So this was, remember, it was from mapping R2 to R2. So this was from a plane to a plane to another plane. But now, and I'm not going to go into too much detail here, it's just good to know, but a change of variables, okay, in 3 variables. Now, anytime, it's kind of a general rule, whenever you're adding on more variables, things tend to get more complicated. Anyways, so change of variables in 3 variables looks like something like this. So I'll just give you a general overview of it. So now we're working with triple integral, right, because 3 variables. And we're integrating over a region W, like we have been doing. So f of x, y, z, and then we have our dz, dy, dx, or any order, really, for the differentials. But now, what we have, so this W, this region, corresponds to x, y, and z. But now what we'll have is a new region defined by u, v, and w. So this here, moving from w to w naught, that's a change of variables in itself, okay? So in this case, we would have a g of, so you can move either way, really, right? Just moving the function that gives you the path from one to another, and the vice versa, the other path that moves you from the other back to your original one, those are both inverses, like we just explored. But anyways, so let's say we want to take a point from w naught and send it into x, y, and z. So that means you take your point, this is your function that allows you to do it, and that gives you some x that depends on u, v, and w, some y that depends on u, v, and w, and finally some z, which depends on u, v, and w. Okay, so basically, taking whatever point this is, you're determining your x, y, and z coordinates. Okay, so in this case, the Jacobian of g, it's really complicated, not super complicated, it just deals with a 3 by 3 matrix, but I'll just abbreviate it here. So Jacobian of g, that is what you would use as your change in volume in this case, not change in area anymore. Area is a two-dimensional quantity, but now we're going to have a 3-dimensional quantity, right? So what actually happens is that, I'll write it on the next slide. So what we have is our triple integral over w. So I'm just going to start with the normal x, y, z, what we've been doing. So this is going to equal the following. So we'll have triple integral over w naught. So this is where u, v, w exist, right? So the bounds here would be the restrictions on u, v, and w. And as far as the x, y, and z are concerned, these are going to be determined by u, v, w points now. U, v, w takes up some space, but as I said, the more you add on variables, the more complicated and lengthy things get. So anyways, so we have that. That's the first part. And then we have the all-important Jacobian. Okay. And you can look in your book to see the actual setup. I don't know. I mean, I don't think it's super stressed. Well, at least when I took this class, we didn't really have to do change of variables in 3 dimensions. The only case where this occurred is the spherical coordinates. Okay, and oh, I should write that. That's okay. That is supposed to be a W at the end there. I got distracted. I'll just leave it like that. So this is the complete formula for change of variables in 3 dimensions. So this is the 3-dimensional version. And one important case, like I was going to say, so important case is from rectangular to spherical, because this will pretty much pop up everywhere you see a triple integral, or at least in the future of this class. So in this case, the Jacobian is the following. So Jacobian of the three-dimensional case is rho squared sine phi. And this definitely should look familiar to you because this appeared in the differential volume, right? So remember, we would have dv equals rho squared sine phi d rho d phi d theta. Okay, remember that? So this is, again, like your r dr d theta for both polar and cylindrical. This r and this rho squared sine phi alike, they're both computed from the Jacobian. Okay, so that's an important case. I think that this is pretty much the most important thing you should take out of change variables in 3 dimensions. Okay, so that concludes this video, and I'll talk to you later in the homework videos, or the practice problems videos if you watch.